Hey everyone, I just wanted to review a little bit of what we talked about on Thursday about water and why it's so unique, like what an interesting and different substance it is. So let's go ahead and take a look at water. What do you remember about its chemical formula? Hopefully you remember that it's H2O, and so that means for every oxygen there are two hydrogen atoms. Now, why is that? Well, oxygen, recall, is atomic number 8, meaning it has 8 protons in its nucleus and 8 electrons in total. Whereas hydrogen over here is atomic number 1. It has 1 proton in its nucleus and only 1 electron. So I tried to draw that here. Now remember that 2 electrons can fit on the first energy level, and 8 can fit on the second energy level. So every atom is trying to get a full outer energy level. So for hydrogen, its outer energy level is the first one. It only needs 2, so it needs to get 1 more. For oxygen, its outer energy level is the second energy level, and that one can hold 8. And right now it has 1, 2, 3, 4, 5, 6, so it needs 2 more. And oxygen is very reactive. It's what we say very electronegative. It will pull electrons. It wants those 2 more very much to be stable. So it has a high electronegativity, a high affinity for electrons, and it will pull them from just about anywhere. So any hydrogens nearby will be pulled towards the oxygen. And it's going to require how many hydrogens to fill the second energy level? Hopefully you said 2, because each hydrogen can only give 1 electron, so you're going to need 2. Okay, so it's not a full transfer of electrons like we saw in ionic bonding. This is what's called covalent bonding. And in this case, the atoms are sharing electrons. So here's hydrogen. It has its own electron, and then it got close enough to oxygen to share this one. So now the hydrogen is full with these 2 electrons, 1 of its own and 1 shared from oxygen. Same with this hydrogen. The oxygen already had 6 of its own, and it's considering the 2 electrons from hydrogen as shared to make it have 8, and it will be have a full outer shell. So they're locked together in this really strong covalent bond that makes H2O. For every 1 oxygen, 2 hydrogens. Unlike in some other molecules that are called nonpolar, these electrons are not shared equally between the 2 atoms. Hydrogen does not have the same ability to hold the electrons as oxygen does. And to understand that, you have to understand that electrons have a negative charge. They're abbreviated E- to show that they have a negative charge. And protons in the nucleus have a positive charge. So they're abbreviated P+ for their positive, for protons and positive charge. So when you think about that opposite charges attract, these 8 protons in oxygen's nucleus are more able to pull the electrons towards it, the oxygen atom, than the 1 proton in hydrogen is able to pull electrons towards it. And so we represent it in this way to help us see that the electrons are spending more time around the oxygen atom. And because electrons have a negative charge, they're making that part of the molecule, of the water molecule, of the H2O, have a slightly more negative charge. So I'm trying to show that here with these sort of colorful blurbs. All of the electrons spend more time or are more closely pulled towards the oxygen part of the water molecule. And so they lend sort of like a negative charge down here or on the oxygen side. Whereas here we have an exposed proton, right? Here's a positively charged proton. And this is the hydrogen, this is the hydrogen. That's making this side, the hydrogen side, slightly positively charged. So what this does is it makes the molecule have two poles, a positive pole wherever the hydrogens are, and a negative pole, a slightly negatively charged pole wherever the oxygen is. So think about it like magnets have poles, a north or a positive and a negative pole. Our Earth has a north pole and a south pole. It doesn't have to do with cold. It just has to do with opposite, in this case, opposite charged regions. Now, would this be the case if we had, let's say, two oxygen atoms? Would one side be able to attract electrons more than the other? No, because they're the same atom, so neither side can pull electrons any more than another side. So anytime you have a molecule that's made up of only one type of atom, like here N2, nitrogen gas, oxygen gas, hydrogen gas, any of those diatomics, it's nonpolar. There's no like side here. One side's polar and one side's not. Even in something like carbon and oxygen, wait a second, we said oxygen is really electronegative. It can pull electrons towards it more than most other atoms. But in carbon dioxide, CO2, that pole is offset because of the shape of the molecule by equally pulled electrons in this direction. So here you can actually have a polar bond, but a non-polar molecule overall, because the two poles, we couldn't cut this molecule and say, here's the negative side, here's the positive side. The negative sides are on the outside and the carbon is in the middle. So we'll look at that a little bit more, but the other one I wanted to talk about is carbon hydrogens, because we're gonna look at those a lot. And so things like fats, oils, anything with these long hydrocarbons are nonpolar. There's no difference in the ability to pull electrons. Okay, back to water. One thing just about notation is it's not a full transfer of electrons the way ions are. So instead of writing just the plus symbol for the hydrogen and the minus symbol for the oxygen, we use what's called a lowercase delta symbol, and that's a Greek letter, lowercase Greek letter that means slightly. So it's not a full, like the electron hasn't been transferred. We don't have an ion here, but we have a partially positive pole on the hydrogens and a partially negative pole on the oxygens. Okay, so what? Who cares? And this gets into that emergent properties part we talked about. So one water molecule is polar, but new properties emerge when you get multiple water molecules together because of this polarity, because of this these differences in charges, you're going to see interactions and the way the molecules arrange themselves in space, attractions between different water molecules. Okay, so you're never just going to have one water molecule by itself. Instead, we want to be thinking about millions of water molecules interacting together. And so that's diagrammed here. And so how do you think multiple water molecules will interact with one another? Now we're not talking about covalent bonds. We're not talking about the bonds that hold a single molecule together. We're talking about interactions between different molecules. And so remembering that opposite charges attract, here the hydrogens are in gray. If you build molecules, they'll be the white little balls that you put on. The hydrogens have a partially positive charge, and so they'll be attracted to a partially negatively charged oxygen of a different water molecule. So just think about that. It's not just going to be like molecules interacting in their own space. Because of the polarity of water, you'll have attractions between different water molecules. And that is going to give rise to these unique properties of water. that's the argument I'm going to try to make. I'm going to try to sell you on, okay? So let's take a look at, well, I asked you to draw these in class, and most people did a great job. They were able to sketch in, okay, I know that the bonds that hold the water molecule together are called covalent. Electrons are being shared, valence electrons are being shared in that, and it's not an even sharing, so it's called a polar, creates poles. But the interactions between multiple different water molecules are called hydrogen bonds. And they're much weaker than covalent bonds. They're much weaker than covalent bonds because they're just temporary attractions. As the water molecules are passing by one another, they're attracted to the different parts. So they're not super strong, but they do still play an important role in giving water its unique properties. All right, so here are those 4 properties that I'm going to try to sell you on that are all directly related to water's polarity. And in 3 of the 4 cases, then the hydrogen bonding that emerges from that polarity. So I'm going to talk about cohesion and adhesion, temperature moderation, water's density as a solid, and then its ability to dissolve. Okay, here we go. So we talked about hydrogen bonds, and we talked about how that makes water molecules attract different water molecules more attracted to each other than if they weren't polar. So if none of, let's just imagine these are oil molecules or nitrogen gas molecules or some non-polar molecule that doesn't have any charges to it, it won't have any attraction to the other molecules nearby it. They'll be together because they're all getting poured together, or they're in one space together, but they won't be held together by these intermolecular forces, these attractions between different water molecules. And so because of this, cohesion, which is water's attraction to itself, to different water molecules through hydrogen bonding, you get surface tension. And you saw this with the astronaut at the International Space Station. Hopefully you saw it with the drops on your penny, how water was more attracted to itself, to other water molecules than to falling off the edge of the penny. You can also see it in surface tension with things like the water strider, which I see a lot of around my house. I don't see a lot of water spiders around my house, but you see it there. And then if you've ever seen the basilisk lizard, this lizard that can walk on water.
Costa Rican basilisk lizards are looking for food. Basilisks have been nicknamed the Jesus Christ lizard. Why? This adult male, probably the father of the young lizards, can't tell us. Nor can this female, exclusive property of the territorial male. It has nothing to do with the feeding habits of the basilisk, which consists primarily of insects and berries. This predatory reptile will help reveal the secret as it stalks the young basilisk.
All right, so it took a little while getting there, but you see that the water is so tightly coherent to itself, to other water molecules, that something could actually walk across it, right? Even something as heavy as a lizard. Okay, so that's cohesion. And that's going to play a role in capillary action. The other part that's important in capillary action is adhesion. So cohesion is water hydrogen bonding to other water molecules. Adhesion is when something sticks to something different, like, oh, I'm going to adhere this poster to the wall, right? So adhesion in this case is water hydrogen bonding to some other substance, not water. And so like we see it in the lab, when you like reading a meniscus, see how the water level is lower in the middle? It's because the hydrogen bonds actually attract the water to the glass up the sides, and kind of like makes it start crawling up the sides of the glass. Okay, great, real cool. But for crawling up plants, it is really important for life on Earth because that's how plants get water, and we all rely on plants at some level. So here, this is a great little diagram coming up where you can see cohesion, water, hydrogen bonds attracted to itself, the slightly positive hydrogen is attracted to the slightly negative oxygen, and then adhesion, the slightly negative oxygen is attracted to or hydrogen bonded to some positive charge in the these types of cells are called xylem. It's the tissue of the plant where water and other dissolved minerals move up a plant. Okay, against gravity, so it's pretty cool. All right, number 2, who cares, why is water so special? Again, the ability of temperature moderation is huge in water. So here, I like this little sim because it shows that in order to raise the temperature of water, these hydrogen bonds, these little dots between different water molecules have to be disrupted. And so it takes more energy to raise the temperature of water than it does to raise the temperature of air, or the temperature of oil, or the temperature of other non-polar substances. It takes much more energy to get water, let's say, from a liquid state to a gas state. And so who cares? Why is, sorry, the fire alarm started going off at school. So who cares? Why is this important? Well, I'm 60 to 70% water, so are you. We don't want the water in our bodies to be just really just like changing, fluctuating rapidly. We want it to stay at about the same temperature, even if we go out into a hot day where the air is hot, even if we go swimming in a really cold pool. Like, we want our water level to stay at about the same temperature. And those hydrogen bonds help keep it stable. They help keep it from releasing too much energy or absorbing too much energy. They help to stabilize. And here's another example, just like bodies of water don't heat up as quickly as the air surrounding them. And that's good because, again, it has a moderating effect on life. Okay, number 3, show it didn't melt. Who cares if ice floats on water? I'd rather have my ice sink in my glass. Well, it's about more than just our drinking preferences, right? So most solids sink in their, like most solids are more dense. And if you can look at the data from the group, they looked at, the density of liquid aluminum versus solid aluminum, the density of liquid oil versus solid oil, the density of liquid nitrogen versus solid nitrogen. Most things are more dense as solids. The particles are more closely clustered together, and so they would sink. But water isn't that way. It's one of the only unique substances that actually, as a solid in ice, it's less dense. The molecules are less tightly packed than in a liquid, and that's really unique. Now, why is this? Well, what happens is the hydrogen bonds, up until about 4 degrees Celsius, they spread out. They stabilize in this crystal lattice structure in which each water molecule is participating in just about the maximum of 4 hydrogen bonds. And remember, you drew that back on your Nearpod or your warm-up. This is the maximum. Each water molecule could hydrogen bond with up to 4 other water molecules. But usually they're moving so quickly, and again, this is a 2-dimensional representation, so it's not the best, but usually they're moving so quickly that they're not always surrounded by 4 others. In ice, though, things slow down, the molecules aren't moving as quickly, and they kind of lock into this position where they have 4 other water molecules around them, and they freeze there. And this creates a crystal structure, which is ice crystals. Whereas in the liquid, they're only really bonded to maybe on average 2, maybe 2 to 3 other water molecules, so they can be more densely packed. So who cares? Again, like, I'd rather have my ice sink. It's a big deal for life because if ice did sink in water, then water would likely freeze from the bottom up, or any ice that did form would sink. And so nothing could ever get a hold. Like no grass could grow in a winter, no plants could survive. Like life wouldn't be possible if everything, if water, if water was more dense in its solid state. And so this is pretty cool. All right, last one. Water is sometimes called the universal solvent. Okay, it can't dissolve. A solvent is something that dissolves something else. Water isn't universal. It can't dissolve everything, but it is pretty much, it can dissolve any other polar substance and any ionic substance. So that makes it able to dissolve a lot. And here's an example of how does it work, how does it do it. So here's some salt put into water. And you remember that sodium chloride salt is an ion. So it has a positively charged ion and a negatively charged ion. And you guessed it, water gets in there and separates this salt crystal. Again, it's a crystal structure because look at the arrangement. And it's like all the positively charged hydrogens like surround the negative chloride ion, and they're like, psh, away from the rest of it. You're dissolved now, right? You're surrounded by water. You've been dissolved. And the positively charged sodium up here is surrounded by the partially negatively charged oxygens. It's like, psh, you're dissolved from the crystal. Like you're waters now. Like you've been totally dissolved, right? So here's an example of what water does to ionic compounds. It can also do this even with large molecules that have some polar part to them. So like I'm thinking like sugar. It's not fully polar. It has a lot of carbons and hydrogens, but there are some OH, there are some oxygen and hydrogen groups on it that stick out. And so water will surround those and dissolve them. Sugar doesn't dissolve as well as salt and water, but it still does dissolve, right? Especially if you heat it up and get the molecules moving really quickly. Now here's a protein. Here's a very large molecule, way bigger than sugar. And still, the water, because of its polarity, this time not quite as much as hydrogen bonding, but they're trying to show it here. Because of its polarity, as long as there's some polar parts on this protein, the water is going to be attracted to them and lock on and surround it and help dissolve it. So there's a little sim that I linked. I'll share these slides with you. There's a little sim linked in the Water is a Solvent of Life where you can play with, if you wanted to, you could play with like just trying to visualize this. So you can change the polarity. So if we have all non-polar molecules, let's just say like oil and, you know, fat or something like that, they don't really have much attraction to each other. There's no charges here at all, right? And then let's say let's try like water. The polar one you can see is the one with the charges now. And the oil will keep that. Interesting. We'll keep that as the gray, I guess. And so something like, you know, why doesn't water dissolve oil? The water's partial charges, the blue and red parts, are so attracted to themselves that they don't really have any time for interaction. They don't have any reason to interact with the oil. Now you could shake it, like I'm thinking balsamic vinegar and oil or something like a salad dressing. You can force them to mix, but eventually the water's polarity is going to make it so attracted to itself, so cohesive, that it'll separate from the rest. And then you could try, you don't show the charge shading, you could make both molecules polar. You could, you know, you can play with the polarity and just kind of see how it interacts. Okay, please let me know if you have any questions. I'll put together a couple follow-up questions so you can check and see how you did. And thanks so much for tuning in.